Welcome to CS70 Spring 2018, Discussion 11B, Problem 3. Problem 3 talks about hypothesis testing, something commonly done in statistics and one of the most common uses of the central limit theorem. Let's take a minute to read the question setup, which says that we will be flipping a coin with some bias 100 times. We don't know what the bias is, but we want to comment on whether it's a fair coin or not, right? So the setup is as follows. We have 100 flips of a coin. Each flip is either tails or heads with some probability. So this is with probability 1 minus p and with probability p. And each of the coin flips are independent. And what we observe is the sum of the number of heads, which by our old trick of writing this as a sum of indicator random variables, is this. And based on what y is, we want to comment on whether the coin was fair or not. So let's list out a few things intuitively. Well, if the coin was fair, y would be close to 1/2 of 100, which is 50. However, we wouldn't be too surprised if y was, say, 51 or 49. However, if the coin was fair, but y was 90, we would be very, very surprised. So the setup is, we know that for the coin to be fair, y is going to be in some range of 50, which is denoted like so. So this is if coin is fair. And intuitively, the more times we flip, the tighter the bound would be. So numerically, what we want is a tight bound of C. And based on that, we will either reject the hypothesis that the coin is fair or accept the hypothesis that the coin is fair. Thus, for example, if we solve the whole problem and C comes out to be, for example, 5, we would say that the coin is fair if we see between 45 to 55 heads. Okay, but mathematically, what are we trying to say? Since we're working with probabilities, what we want is that the probability we are wrong is low, which means the probability that we reject the hypothesis, if it is in fact true, that probability should be low. And numerically in the question, we want that to be less than 0.05. So what we're going to do is we're going to compute a C, which corresponds to a 5% probability event of the fair coin giving us more than this range of heads. So what we're going to say is we'll find a bound such that 95% of the times my fair coin would be in that range. Okay, so numerically, what am I looking for? I want the probability that the number of heads I see, capital Y, minus 50 in absolute value is within a range of C of 50. And you can correspond that these two, in fact, are equivalent statements. I want this to be at least 95%. And I want to compute the C that corresponds to this. OK, well, now if we use an approximation and we say, look, y is the sum of n draws of independent random variables, well, then by the central limit theorem, y converges to a normal with mean of n times the mean of one of these guys, which if we assume a fair coin is 1/2, and a variance n times sigma squared, which again, if we assume a fair coin, is 1/4. Okay. Numerically, this is saying y is a normal on 50 and variance of 25. So we now have that y is approximately this. And further, by the fact that it is normal around 50, it has a distribution something like this. And we want to compute a C such that in this region, I have 95% probability. Well, okay, if that's the quantity I'm interested in, this should be greater than or equal to 95%. Well, y minus 50 is a normal random variable on 0 and 25. So I can further divide and say, well, this is equivalent to the probability y minus 50 over 5 is less than or equal to c over 5. And why do I do this? Well, now this thing, I'm going to call it, say, z. This is now a normal on 0 and 1. Because remember, dividing by a factor of x changes the variance by x squared. Okay, now that this is true, what I really want is for a standard 0, 1 normal, I want to find a constant c such that within this region, this probability is greater than or equal to 95%. Now, for any given c, the probability from here all the way to the end here corresponds to phi of c. So remember, phi of c represents the whole thing. Similarly, so this is phi of c. Similarly, phi of negative c represents this whole thing. So this is phi of negative c. And in all of these, this is capital phi, which is the CDF of the standard normal, not the density. And in all of this, remember, capital phi is the CDF of the normal distribution, not the PDF. Okay, so phi of negative c corresponds to this region here. Then the middle center region will correspond to phi of c minus phi of negative c. And I want this to be greater than or equal to 95%. I'm sorry, this is c over 5. Because remember, we made the change to c over 5. So now I have reduced the problem of finding what's called my confidence interval to this. I want to solve for this equation. However, remember that I don't actually have a function for capital phi, but we'll see what to do about that in a minute. For now, I will make one final observation, which is that phi of negative c over 5 is exactly equal to, for c over 5, the region to its right. Remember, the normal is symmetric about the origin, so to the left of minus c over 5 is the same as to the right of c over 5, which implies phi of negative c over 5 is equal to 1 minus phi of c over 5. Because remember, phi represents the area to the left, so the area to the right is 1 minus that. Okay, now that this is there, I can simplify this equation, so star, to now say phi of c over 5 minus 1 minus phi of c over 5 should be greater than or equal to 95%, which is the same thing as 2 times phi of c over 5 should be greater than 1.95, which is the same as phi of c over 5 should be greater than or equal to 0.975. Okay, now comes the actual problem of how do I solve this equation. Well, now we use what's called the standard normal distributions table, and I look for a number in here corresponding to 0.975. So I see that somewhere here, when I have c over 5 to be 1.96, that the required probability is fulfilled. So remember, what I did was I looked for a number in this table, which was 0.975, because this table is just pre-computed phi values for different values of your input. And finally, if C over 5 is greater than or equal to 1.96, that corresponds to C being greater than or equal to 5 times 1.96, which is 9.83. And this is, I can say, approximately 10, which essentially says, now finally going back to the original setup, that if y is between 50 minus roughly 10 and 50 plus roughly 10, I can conclude that with 95% probability, it was a fair coin. Intuitively, if y belonged to 40 to 60, the coin was fair with 95% probability. And if it was outside this, with only 5% chance of error, the coin was not fair.